Hello, welcome to this presentation. My name is Maria Andrade. I am from Universidade Federal de Sergipe in the Northeast in Brazil. I am professor and today I will talk about some gaps results for free boundary CMC surface. Okay, this is a joint work with Ezequiel Barbosa and Edno Pereira. This work was financial support by CNPq FATEC Sergipe, Brazil. First, I would like to thank you very much, the organizer, for this opportunity. Marcos Petrus Cavalcanti, José Miguel Mazzani, Rojo Lee. This is a very good special section. Well, in this presentation, I will talk about, in the first moment, about some introduction, motivation in the problem. Then you have some gap results, and you give some ideas about this problem. Okay? Let's go to start. First, we start with motivation and introduction. Then, in this moment, I will talk about some classical results about CMC surface in the Euclidean spaces. Then, I will talk, after this, I will talk about free boundary problem. Okay? Let's go to start. Gelé showed that any closed start shape CMC surface in the Euclidean space in the dimension 3 is around the sphere. He proved that. Then Hoff provide that enclosing enmeshed CMC topology to a sphere in the Euclidean space is around the sphere. In this moment here, Hoff conjecture. It's possible to remove this hypothesis topology to a sphere. This is possible. These are famous conjecture. These are conjecture, Hoff conjecture. Okay? So, Hoff conjecture the condition of topology to a sphere can be removed. After this, we give some result in this context, okay, to introduce this problem. Okay. Alexandrov gave an affirmative answer to Hoff conjecture. But in this case, he assumed that the surface is embedded. Okay. In this moment, he invited the Alexandrov the reflection method or movie plane method. This method is very important in some cases, some results in geometry, different geometry. Okay. And Barbosa do Caso provide us a special and beautiful results about closed immersion stable CMC hypersurface, and he proved that all closed immersion stable CMC hypersurfaces is around the ball. He established means that the second variation of the area functional is non-negative. What does mean? Area is bigger than 0 for any volume preserved variation. Then his Young and your collaborator construct a CMC topological three-sphere in the space Euclidean dimension 4, which not round. After, went constructed a CMC of two torus in the Euclidean space in dimension 3, which disproved Hoff conjecture. Okay? Finally, Capules shows that there is CMC mesh of compact surface of any genre. here in this moment, I will give some reference for students, special students, that you can see more information about this. This reference is very good in this point. Okay. Well, give this some information, some motivation about this problem in the context in CMC surface. You give the definition about field boundary problem. Okay, let's consider immersion x to sigma to m, immersion, isometric immersion, where sigma is a smooth compact, so that the boundary of sigma is in boundary of m. You say that sigma is phi boundary, CMC surface, if the mean curvature is constant and sigma is orthogonal to the boundary of n. In this picture here, in the left, you have the ball here. You have the ball B3. We have the disc. What does mean the disc? You have this ball. Imagine this ball, for example, and you have the disc. What the disc? You have the plane. For example, Z is to 0. You have the ball, you have the plane. Then when you intersect the ball with the plane, you have this disc, this 0. This disc, this 0, is a free boundary minimal surface in the ball. But if you have another plane, for example, this plane here, Z is to K, where K is not 0, you have this intersection, where the intersection is a disc with which intersect the ball with angle different, not orthogonal. Okay? So in this case, you have this disc is a capillary minimal surface in the ball. Okay. But if you want to define the free boundary problem, you can use the first variation formula. You remember the first variation formula is given for this expression where H is the mean curvature. So you have that the surface is free boundary if H is constant and this integral is 0. So this means is equivalent to talk about free boundary problem is the same to meet the critical point of variation formula, the first variation formula. That's me. The first variation formula is 0 if, only if, H is constant and sigma is orthogonal to the boundary of M. So you can introduce the free boundary problem in the same context of problem of variation. Okay? Well, let's continue. Motivated by this definition, motivated for the first introduction, you have some results here provided by Rose Vergastas, which say Rose Vergastas studies compact stable CMC hypersurface with free boundary in the ball, and they proved the next results. Let be a closed ball and consider sigma in this ball, which is immersed, orientable, compact, stable, in the same way that you define in the context result Barbosa and do Carmo, and the surface is CMC with boundary. Then they proved the boundary of sigma is embedded, and the only possibles of sigma are. The first one is sigma is a totally geodesic disk. Sigma is totally disk. Sigma is a cap, spherical cap, okay? Or sigma has general one with a two, at most two boundary components. Here, in this moment, you have an important question. Is possible to remove the last one, it? Is possible to remove this? Well, this question was answered by Evaldo Nunes, which proved the results. Nunes provided the results. Let be a ball, a closed ball. You consider sigma in the ball, which is a masked, orientable, compact, stable, semi-C surface with a boundary. Then sigma has general 0. What does mean? That does mean that the it3, the last it, you can remove it. So sigma, in this context, with this hypothesis, what have we? We have that sigma is a total geodesic disk, or sigma is a spherical cap. Okay? Let's continue. So now I will talk about gap results. In this here, I will remember some important results which was provided by Chern, do Carmo Kobayashi, and also by Lanso. Okay? In this context here, you have a classic result about minimum hypersurface in the sphere. So let's consider sigma be a minimal compact hypersurface in the sphere. Suppose that the second fundamental form A satisfies this gap. Okay, then what does mean? Sigma is an equatorial disk in the sphere, or sigma is a Clifford torus. So in this moment here, you have this gap. Okay, when you talk about gap, about something, in this context here, you think about the second fundamental form that satisfies some inequality, in this case, a gap. After this, a question, natural question about this is possible to do the same problem in the classical minimal surface in the sphere? Is possible to do in the context of free boundary? Yes or not? Yes, you can do this. This problem was provided by did by Ambrosio Nunes, and they proved this result, that sigma compact free boundary minimal surface in the ball, in the triaquidal ball. Suppose that the second fundamental form satisfies this gap. Remember, here you have the hypothesis that sigma is free boundary. So it's natural you consider the support function, here defined by x and the vector normal vector, okay? And why here you have 2? Motivated por this result, here you have the dimension of sigma is n. So in the context, it's natural you have number 2 here. They provide that either this in the left is 2, 0, and sigma is a flat equatorial disk, or the equality here, the equality satisfies the equality, and some point is sigma is a critical catenoid. So you remember here in this gap, this is bigger than 0. What this proved? Oh, this gap here, and the second fundamental formula is 0, or there is some point where this gap here, this function, satisfies the number 2. Okay? But what does mean the equatorial disk? Remember, you have the ball, the Euclidean ball, then you have the plane, you intersect the ball with the plane. What the plane here, z is equal to 0. Then these are equatorial disk. Okay? And the disk is free boundary too. Critical catenoid is annals, okay, which this intersection the boundary of the ball with orthogonal, okay. And then we talk about the very nice, very important result about rigid result. This result which is proved by Nietzsche, which we can explain more. Let sigma a compact free boundary minimal surface in the ball. If sigma is topologically equivalent a disk, then sigma is a plane equatorial disk. So these are rigid results. Okay. After this, you can talk more about very beautiful conjecture which was did by Fraser and Lee, which this conjecture say the critical catenoid is the only embodied free boundary minimum annals in the ball, in the Euclidean ball, up to region motion. Okay. Then, in this moment, there are some partial answer, but not all complete answer. Okay. If you remember in the context of classical results in the minimum surface, the Luss conjecture that the Cliff torus is the only by the minimum torus in the sphere up to region motions. Okay, in this context, minimum context in the sphere. It was proved by Simon Brundle in these papers, in this work. Okay, so after this, after the work on Ambrose Nunes, it's natural to ask about is possible to do this work Ambrose Nunes about CMC surface. This problem was provided by Barbosa, Cavalcante, and Pereira. Let's go to the results. Let sigma be a compact free boundary CMC surface in the ball. Suppose that all the points in sigma satisfy this gap. Remember that Ambrose Nunes give this gap xn is that true, but Ambrose Nunes work with minimal surface. Here, Barbosa, Cavalcante, Pereira work with CMC surface. So, what's the first problem here? The first problem here is meet the gap. Okay? After we meet the gap, you have some problem, but the first problem here is the gap. So, if you have the all points in sigma satisfy this gap, where this symbol H with circle satisfy this, what does it mean? The second form with the trace, then O in the left is equal to 0, and sigma is a spherical cap, or equality in this occur in some points, and sigma is on the Delaunay surface. So, remember, in this left here, 0, this satisfies this inequality. So, all this happen, and this satisfies is to 0, is equal to 0, and sigma is a spherical cap, or the equality is, this equality is satisfying some point, and they prove that this is a part of the Delaunay surface. So, in this picture here, you can see in the left the ball, and the green here, a spherical cap, and the right here, you can see the ball, and you have here a catenoid critical, okay? To illustrate these results. Well, what's the idea? The idea of the proof is inspired by work of Ambrose and Nunes. First, you consider the analyze the function, distance function, restricted to surface. Well, what does that mean? What's the idea? What's the problem here? The first problem is you need to find the correct condition, which generalize the gap condition Ambrose Nunes. It's the first problem. After this, you need to guarantee that the gap implies that the Hessian of the function phi is big or is equal to 0. What does mean this? You have the function, the operator Hessian, does mean that the value of this operator, lambda 1 is bigger than 0, and the lambda 2 is big or equal to 0. Okay, it's equivalent. But to prove this, one big important point here is that the CMC surfaces have complex structure. Okay, in this point here is essential this characteristics. After this, you need to have the gap. After this, you need to guarantee that the condition implies the ratio satisfies this condition. Then you need to prove that all there are some rotations MC annons in the unit Euclidean ball. So 3 points here complete all the proof. This proof is inspired by Ambrose and Nunes. So in the first moment here, I talk about some idea with this proof, okay? So I stop here in this lecture. I hope that you will enjoy this lecture. In this next lecture, I will talk about some results and that I and my collaborator did. Okay? I hope see you later. Bye bye.